This is about computing correctly with inductive relations, and this is work that Zoe, Aaron, and I did over the last couple of years. Unlike Ryan, I am Greek, so I like Greek letters, and two of them are on the first slide. So imagine your favorite typing relation in whatever language, for whatever language you want. And the question I'm going to ask to get started is, how would you represent this if you were to mechanize it? So if you wanted to mechanize a typing relation in whatever proof standard of your choice, for me, that's the coq, but imagine whatever, how would you represent it? Well, by and large, there are two ways to do that. The first one is to represent it as a function. You write a function that takes three inputs, a type environment, an expression, and a type, and gives you back a Boolean that decides whether the things are well-typed, the term is well-typed. The other way is to write an inductive relation. Again, it takes three inputs, environment, expression, and type, and you construct a proof using constructors, using inductives that the typing relation holds. Now, these have relatively complementary advantages and disadvantages, right? On the one hand, if you write a function, you can compute with it. And what does that mean for me in particular? It means you can test it. On the other hand, if you have an inductive relation, you can model a lot more behaviors, like non-termination and non-determinism. And at the same time, it facilitates inductive reasoning, because when you write an inductive relation, you get these really beautiful elimination and induction principles that come along with it in a proof assistant like coq. So a lot of people end up having to write both if you want to use both benefits, and then you have to prove that one corresponds to the other, and then maintain that correspondence, and that's just a pain. So the idea behind this work is, could you just get away with writing one of them? Could we just get the inductive relations and extract computational content out of those? Well, since I'm here, the answer is yes, but instead of showing you abstract stuff, I'm just going to walk you through a running example of simply type lambda calculus and how the whole thing works. So when I say simply type lambda calculus, I just mean standard lambda calculus with natural numbers as the base type, and we only have numbers and addition as the base type operation. So as simple as I could possibly make it. And in fact, to make it even more simple, let's ignore everything else and talk about a language that just has numbers. So our language has numbers, and the type is integers, or naturals. So there's one typing relation here. The typing relation is that all natural numbers have the type of natural numbers. And we can represent that as an inductive type, saying that for every environment, our integers have type integers, or naturals, or whatever you want to call them. I'll use the term interchangeably because it doesn't matter for this talk. Now, if I were to ask you to write a type checker for this language, you could probably do it very quickly. You can just write a recursive function that takes three things, and then somehow you have to decide if the term has the correct type. How would you do that? Well, you probably need to do a pattern match. Against what? You look at the conclusion of your inductive, of your constructor, and it says that the expression has to have the form integer, and the type has to have the form tint. And that's exactly the pattern you match against. And then you're done. Integers have type tint, everything else doesn't. Great. So let's keep going. What if we added another typing judgment in our language? Addition. Well, we extend our typing relation with a constructor that says that if E1 is an integer and E2 is an integer, then the addition is also an integer. And if you could guess, you add an extra pattern match in your fixed point. What do we match against? Well, we look again at the conclusion of the new rule, and you have an addition if we wanted to, and then the integer again. Now, there are two more things you have to take care of now. There are preconditions, there are premises to your constructor, and the only thing you can do is recursively call the type checker to make sure that E1 has the correct type and E2 has the correct type. So it seems like everything works pretty well. And in fact, this procedure that I mentioned, make everything a pattern and then recursively call, works for a surprisingly large number of inductive relations. But of course, I've carefully avoided everything interesting about inductive relations, like non-termination or non-determinism. So yeah, something's off. In particular, the problem comes in, why do these recursive calls terminate? And in fact, they normally wouldn't. And secondly, why do these pattern matches not overlap? Because when you have non-determinism, these will overlap. So what we're going to do is derive semi-decision procedures where we do the straightforward thing of we're adding a natural number as fuel to make sure that things always terminate, to have a total function, and we change our result to be an option bool, where in standard total function practice, the non will mean that we need more fuel to decide whether the typing relation holds. And then to handle non-determinism, instead of having one big pattern match for every possible constructor, we have handlers for every possible constructor, where each handler basically decides whether a particular constructor can be used to conclude the typing relation. So what does these handlers look like? They're very similar to the matches we saw before. So for example, for the integers, the handler is just a pattern match that returns some true or some false. If it has the correct form, as described by the conclusion of the tint constructor, and some false there when the handler fails, it means that tint cannot be used to conclude the typing relation, but you can follow through to the next handler for the next constructor until you hit some point. So you're basically doing a backtracking, logic programming-based search until you figure out if any constructors can be used to conclude the typing relation. Now, all well and good, and the same exact thing can work for addition, and I'm just going to show it again. The only thing that changes is that instead of having a Boolean conjunction there, we have to lift it to options because now our recursive calls return option bool. But there's nothing really going on here. It's exactly the same thing as we saw before. So is that it? Are we done? Can we handle every inductive relation we would care about? Well, no. So where do problems come from? Fortunately, lambda calculus showcases every single problem, so let's keep going with abstraction. So lambda abstraction is straightforward. A lambda term has a function type if we extend the environment and the body has the correct type. Now, following the same approach, we could write a pattern match. If it doesn't have the shape we want, we will return some false and let some other handler handle it. But on the other hand, if it does have the correct shape, we can just do a pattern match. Well, no, we can't, because there is a nonlinear pattern there. Inductive relations have nonlinear patterns, and I've been getting away by carefully choosing my early examples to avoid that. So there's something we need to do here, and in this case, we have an easy solution. And the easy solution is we can rewrite those nonlinear patterns on the fly. And in particular, we can just introduce a new variable in our inductive. This is a completely equivalent formulation, assuming you can actually write that equality over there. And all that means is that when you're going to satisfy the premises recursively, you have to make a call to a function that checks whether two types are equal. That does mean you have to have decidable equality or some kind of equality about those things. But thankfully, that can also be derived by the same decision procedure, semi-decision procedure derivation that I've been describing. So all in all, this was not a huge problem. The real problem comes when you start to talk about application. Why? Let's try the same approach to try to mechanically derive our handler for this constructor and see what happens. Like before, we're going to do a pattern match, and this time the pattern match goes through easily. We match on E, we get an application of E1, E2, perfect. And now we go on to handle the two recursive premises. We make a recursive call to type E1 and a recursive call to type E2. But now, T1 is unbound. And there is no amount of clever rewriting that we can do to make this appear. This is essentially an existentially bounded variable for the constructor, and there is no way to determine it uniquely from the conclusion of our rule. So here we have to do something. And this is exactly the same problem that you encounter and solve with bidirectional type checking. You have to synthesize this tau1. And that's exactly what we're going to do. We're going to use exactly the same procedure that we derive a semi-decision procedure for inductive relation, and we're going to derive an enumerator with basically exactly the same structure. So if we had access to an enumerator, then we could enumerate all the types that E1 could get over there, and then go on to check whether E2 has that type. And that would be a pretty valid handler for this particular thing, assuming we had access to an enumerator. So thankfully, we can follow basically exactly the same approach and get such an enumerator. To see how, let's go back to the addition rule and rewrite it a bit to tease out a bit more structure. What do I mean by that? Well, we will rewrite those calls to those recursive calls to typing to be to look a bit more monadic. So what we're going to do is we are operating inside an option monad. And basically, we're making sure that when we call type, the result is some true. Where we make a call to type for E2, the result is some true. And then we return true, where everything here is options. And there are two modes of failure, right? Whenever the typing relation returns none, that means we're out of fuel, and that signifies something different, that when the typing relation fails and returns some false, in which case we return some false out of the whole thing. Okay, so far all I did was a slight rewrite, but now what if we wanted to produce a tau such that this relation holds? Well, first of all, it's no longer an input, so let's remove all of those things away. And now, what we're going to do, we're just going to change the monad. The monad is going to become a list option monad, and the bind is just list option bind. And there are two ways of failing, and we can simply denote those as list of none and empty list for enumeration. And now, all we need to do is follow again the structure of the inductive, make sure that the result of enumerating E1 is the thing that is expected by the shape of the T-add constructor. And at the end, just like we were using the conclusion of the typing relation to figure out what we're matching against, we're just using the conclusion of the typing relation to figure out what we're returning. And really, with just this simple parameterization of a monadic framework, you can get a checker and an enumerator. There's a lot more details than that, and the paper contains a lot more of how this is actually done, but this is the gist of it. You have a very monadic parameterized framework which you instantiate different ways. And what do you get in the end? Well, users write your inductive relation. You can do that. And then we derive, but you write calls like derive some magic incantation for types that satisfy your typing relation, or a decidability procedure that checks whether type holds. And then you get back an enumeration fixed point of the particular type, or a type checker. And since most of my work involves random testing, you can use exactly the same thing with a different parameterization to get a generator for these things. So what's the result? Well, if you wanted to check preservation, for example, you can derive a generator for random terms. You can derive an enumerator for the step relation to see what its steps do. And then you can derive a type checker for the typing relation that internally uses the enumerator for the typing relation in order to test everything automatically. So you get a lot of benefit, in particular in terms of random testing, which was my motivating application. Now, in the time I have left, the title was not computing with inductive relations. It was computing correctly with inductive relations. So where does this correctly come in? Well, we provide automatic proof of correctness for every derived computation. So for every one of those things, we have an LTAC2 script that makes heavy use of metaprogramming to prove soundness and completeness with respect to that inductive relation. Just as an idea of what those statements look like, well, soundness, by soundness, I mean that if the checker says that the property holds, then you can construct a proof of it. And if the checker says that the property doesn't hold, you can construct a proof that it doesn't hold. Hopefully, we can do the same with completeness. So, for example, if we have a proof of a property that doesn't involve any negations, then there exists a fuel that makes the checker say it holds. And at some point, I'd have to stop making good claims because not everything is pretty. And you can't do the reverse. Why can't you do the reverse? Because inductive relations are undecidable, right? And you can not undecidable, but you can't really expect to be able to capture every behavior. So, for example, if you wanted to write 0 as a very weird inductive relation like this, where 0 is in the relation and you have to recursively check something higher, there is no finite fuel that can conclusively decide that a number is non-zero using the procedure I described. Fortunately, we never actually encountered any case like this in our evaluation, so that's what I'm going to talk about next. So what did we care about? We cared about 3 questions. Is it practical? Is it fast enough for testing? And is it useful for anything else? In terms of is it practical, we looked at the Software Foundation series of online textbooks. Right? So we went through the entire first 2 volumes. We grabbed every inductive relation we could find, and that contains relations that are written in a manner that no sensible person should ever write for teaching purposes. And we found out that we could derive every single relation that doesn't involve high-order functions. So ignoring the logic fragment of where you'd have to generate whole logic triples and stuff, basically every single thing that doesn't involve high-order data can be enumerated and checked. Is it fast enough? Well, we want to check if we could use these derived checkers to check the benchmarks that exist in QuickCheck. And the overhead is minimal, right? For a lot of inductive relations, the only price you pay is a couple of matches and a couple of binds overhead, which amounts to less than 2% if you're actually using them for testing. So they're pretty efficient. And finally, in the paper, you can also find a case study on doing a proof by computational reflection, which shows how you can use our derived checkers to perform a proof and speed up the type checking time dramatically. So, of course, the paper has a lot more information. It talks about how you can unify generators and enumerators so that the monadic switch that you do there is easier for implementation purposes. More details on the proofs, more details on evaluation, and everything is available online in QuickCheck. It's implemented in QuickCheck. And with that, I'll take any questions you might have.
Okay, thank you very much. I don't have to go very far.
So usually when I want to compute with a relation in Coq, I just use either repeat constructor or e-constructor or just e-auto. Is it right that this is roughly the same algorithm as what e-auto is going to do?
Yeah, you can basically do that, right? Repeat, apply the correct constructor, and that.
Oh yeah, it's not going to be very fast or efficient, right? I was just wondering whether the algorithm
30 seconds. Yeah. That takes 0.05. So yes, the algorithm is not that much different. It's just logic programming applied to compiling a logic programming thing on top of an inductive relation to extract some semi-decision or semi-producing procedure. But it's actually implemented proof correct and works for Coq for testing.
Thanks for the talk. Can you report on your experience with LTAC2? Was it complete in terms of features?
There was one feature that we would really, really have liked, and Zoe can talk a lot more about it. But it was really good. The meta-programming facilities that it comes with are really a lifesaver in terms of using just LTAC. There was one aspect of the proof derivation that I didn't talk about at all, which is that if we were able to know which rule we are in, we would be able to immediately say, okay, for the different case you're in, just apply this particular proof script. But instead, what we ended up doing, because we didn't have that option, is you try all of the proof script. So it's the proof is quadratic in the number of constructors, but if you had access to the particular case you're in, you could be able to make that linear. But we didn't figure out a way to do that. But in general, LTAC2 was a lifesaver.
Thanks.
Can you say a little bit about the examples at the end? I have a little bit of a hard time imagining what they looked like, and
here.
Yeah.
So,
and what do you correctly compute with them?
Okay, so there are three examples. One is, let me make that large again. Yeah, so there are three examples in the QuickCheck benchmark that allows you to quickly benchmark a few things of interest. One is binary search trees, where the inductive relation is whether a thing is a binary search tree. So you derive a checker for whether something is that. The second one is an information flow control case study. So we had this paper back in ICFP 2013, I want to say, that tests for non-interference. And here the inductive relation is indistinguishability. So if you generate things that are indistinguishable and you check that they're indistinguishable. And then last one is simply timeline calculus, which is the example I was using throughout the paper, where you were testing, I think, preservation of a parallel step reduction property so that you can tease even more bugs out. You can make a lot of bugs there. And you generate and check typing.
Okay, yeah, that helps. Excellent. Okay, any other question? If not, then we are right on time for the end of this section. Thanks again, thanks very much, and this concludes this section.